We just learned about the interactions between molecules on the microscopic scale, but what can we do with that information? Well, it turns out one of the things we can do is calculate the probabilities of certain events taking place. So, for example, down here, let me get a number here. If I start with, let's say, a molecule or a pair of atoms in any case that has some kind of an interaction, a bond or a sticking interaction of some kind, and then I break that interaction, then the energy in the initial state, state 1 here, is going to be lower than the energy in the final state here. You have to put energy in to break the bond. And that means that the change in energy will be, which is always final minus initial, right? Will be a positive quantity. This number is the bigger one. That one's the smaller one. Intuitively, you would expect that when you have to put energy in like this, that energy comes from the surroundings, right? So you're basically taking energy out of the surroundings, putting them into, in this case, this is our system, and that should reduce the number of microstates, reduce the entropy available, and that should therefore be improbable, or we expect it to be improbable. On the other hand, if you go back the other way, now you're forming a bond. That means energy will go back out into the surroundings. That's a spreading process. That will increase the number of microstates available. That should be a probable process. It turns out that in these kinds of cases, there is something called the Boltzmann distribution. I won't derive it here. We will derive it later to come to a better understanding of where these kinds of things come from. For the moment, I'm just going to give you the result, and then we're going to do some examples to see how it works. What the Boltzmann distribution in this case says is that the probability of observing state 2 here, the final state, divided by the probability of observing the initial state, the ratio of the two probabilities that took place during the change, is equal to the exponential of the change in energy divided by this quantity RT. R there is the gas constant. RT is 8.314 times whatever the temperature is, and it represents the available thermal energy. Basically, it represents the amount of energy that's probable to be able to extract from the surroundings in order, say, to break a bond. And therefore, in this case, we can see that if the energy change is positive, like it was up above for breaking a bond, then this whole quantity will be positive. That minus sign will therefore mean that this exponential is less than 1, and that means that this ratio is less than 1, which means that the probability for the final state is lower than the probability for the initial state. In other words, because we had to take energy out of the surroundings, put them into the system, this guy is less likely to be observed than this guy was. On the other hand, if we went back the other way, or if somehow it turns out that this change in energy is negative, which it perfectly well can be, then this whole quantity will be positive, the exponential will be greater than 1, and the final probability will be greater than the initial probability. So depending on the sign of the energy change, the probability can either go up or down for the final state. Also, you can see from this that the amount of energy that matters is controlled by this quantity RT. At a given temperature, let's say at 300 Kelvin, that quantity is about, well, in fact, 8.314 times 300 Kelvin is 2494 joules. So that's, at least at room temperature, that's the quantity of energy that matters. If delta U is much greater than RT, then this exponential will either be an exponential of a big positive quantity or a big negative quantity, which means that one of these two probabilities is much greater than the other one. One of the two probabilities, really, we don't see at all, and the other one is dominant. On the other hand, if delta U is much smaller than RT, then this whole quantity up here is close to 0, and in that case, this ratio is near 1, which means we're going to see both probabilities more or less in some kind of nearly equal ratio. All right, let's do an example. Let's first consider a weak interaction. So two argon atoms, they don't have any charge, they don't have any bond, they have induced dipole interactions, and that's all. I've placed them at 3.4 angstroms apart because that turns out to be the minimum of the Leonard-Jones potential. So we're going to be using the Leonard-Jones potential to calculate the interaction energy between these guys. That's the bond, quote unquote, right? It's not really a bond, it's just a van der Waals interaction, but that's the thing we're breaking. And the depth of that van der Waals interaction is controlled by, where's the actual, there's the function, by this quantity epsilon, and when this distance, the distance between the two argon atoms, is equal to this quantity R0, which in fact is 3.4 angstroms, then this whole quantity is a 1. We get a 1 to the 12th power, which is still a 1. This whole quantity is 1 to the 6th power, which is a 1. So we get 1 minus 2 times 1, which is just minus 1. So this whole thing in brackets is just a minus 1. I set things up that way because it was easy. So that's why I put these guys at the minimum distance for the potential. And now this quantity epsilon, the well depth for the Leonard-Jones potential, is given as a temperature, 120 degrees K, times the gas constant. It turns out that's just a convenience. I could have put it in joules, and we get the right, same answer, in fact. But it's convenient to write things sometimes, to write energies as some temperature times the gas constant. All right, in this case, if epsilon here is 120R, and this stuff in brackets is minus 1, then the energy change is minus 120. Oh, sorry. The energy of this pair when you're in the bonded state at 3.4 angstroms is minus 120R. When you break the bond and put the atoms far apart, then the energy is 0, and so the difference in the energy is 0 minus a minus 3.4, or 120R. Now if we put that into our formula up here, we have the delta U. Let me clear out some of this junk. We have our delta U, we know what our T is, and here we are, so there's the delta U, 120R. And now you can see why it was written as 120R, that energy was. It's because on the bottom we now have R times T, the R's cancel, makes the calculation easy. We get e to the minus 120 over 300, which is just 4/10, or e to the minus 0.4, and that's 0.67, or about 2/3. What that means is that, yes, it's true that this final state, the broken state, is a little less probable. It's a ratio of 2 to 3, right, than the initial state. 2/3 of the time we're going to see this guy, 1/3 of the time we're going to see, well, not really, we'll see later, but less of the time we'll see this guy, but not very much. And the reason why these two guys have pretty close to equal probability is because the interaction is weak. This level of this change in energy is, well, the available thermal energy is 300R, so there's more energy available in the surroundings than there is needed to break the bond. That means all the energy in the surroundings, basically these molecules are going to get collided with and buffeted, and they're going to be shaking around, and there's enough energy in all of that to easily break this bond. And so we see the broken state almost as often as we see the together state. All right, I'm going to skip this next little bit for now. We'll come back to it. Let's do another example now with an actual chemical bond, but a weak one. So the bonding energy for I2 molecules is about 151 kilojoules per mole now, so 151,000 joules. That's much bigger than in the last case. When we break it, the change in energy is going to be plus 151 kilojoules per mole. If we plug that into our formula, delta U is 151,000 over RT 2494, and that gives a value of 5 times 10 to the minus 27. In other words, probability P2 here is 10 to the 27 times smaller than probability P1. That means, okay, in principle, you can see this broken state, but boy, it's really improbable. Virtually all the time, you're going to see the molecules in their bonded state. And of course, this is generally true. This is a weak bond, and even so, the bonds really don't break at room temperature. And so now you see that the difference between something like this van der Waals complex up here, right? This can be considered a molecule of sorts, if you like. It's just a very weak bond. So the difference between that weak interaction, it's called a van der Waals complex, in fact, and a normal chemical bond is really just the strength of the bond. This is a much stronger interaction. And there isn't enough thermal energy right now. There's only about 2,500 joules of available energy, and we need 150,000 joules. So there just isn't anywhere near enough energy in the surroundings to break this bond. Still, occasionally it can happen, but it's going to be rare. All right, let's go back to this business that I skipped a minute ago. We'd like, where am I? Here we are. We'd like to be, we've been calculating the probability ratios, P2 over P1, and that's useful and interesting. Informative is what I was looking for. But we'd like to get these guys independently. We can do that making use of the fact that the two probabilities, there's only two possibilities in this case, right? We're either in the initial state or we're in the final state. And the two of those probabilities have to add up to 1. So we can use this relationship plus this relationship to solve for P1 and P2. Specifically, we can take this relationship for P2 and plug it in there. Now we have a relationship that only depends on P1. We can solve. And if you do, you get this. And the result is that that P1 is equal to 1 plus this exponential factor that we have been using all along. That's just the P2 over P1 ratio, right? So if we calculate that already above, we can just plug that in here, and that's what we're going to do. And for P2, that's just 1 minus P1, right? So you can get these formulas over here, but once you've calculated P1, it's usually easiest just to take 1 minus that to get P2. All right, so if in our first case, this ratio is 0.67, then P1 is 1 plus 0.67, which is about 0.6. 0.2 is 1 minus that, or 0.4. And so we're going to see the dimer form, the van der Waals complex, only about 60% of the time, and the broken form about 40% of the time. On the other hand, if this had been the iodine bond, this probability would be pretty much 100%. It's 0.9999927 times, right? Because it's 10 to the minus 27. And this would be 10 to the minus 27, basically, probability, which means we're going to see the iodine molecules all the time and essentially never the broken ones. So it's basically the same story we got from the ratio, but a little bit more complete information in this case. All right, that is our beginning or first pass at the Boltzmann distribution. Now I want to talk about entropy and the second law. This is now material from Chapter 7 proper. We essentially finished with Chapter 6. And entropy has to do with the second law, has to do with statistics, is essentially the difference between thermodynamics, a statistical theory like thermodynamics, and the more mechanical theories that we are used to, quantum mechanics and classical mechanics. And therefore, this Chapter 7 is near the heart for the whole thermodynamics part of the class. We saw already earlier a little bit of this. We're going to basically expand on this story that we talked about earlier in this next little bit. We saw earlier that if you start with a system that's got all the molecules on one side, you remove the barrier, let them spread out, then the probability of these guys spontaneously going back to this state is really small, 2 to the n power against, where n is the number of molecules. Now we're going to ask a related but somewhat more detailed question. We're going to say, let's suppose we divide the box into two parts with volume V1 and V2. We're going to let the molecules move around at will, but when we do that, we know that we won't always see the same number of molecules in each part of the box. What we'll see are some number of molecules on this side, some number of molecules on this side, and we want to know the probability of seeing N1 molecules on side 1 and N2 molecules on side 2. So we're asking for a whole probability distribution in this case. We're not just asking for one possibility, but every possibility. Let's see if we can derive that. In order to do that, it is useful to be a little bit more rigorous than we were before. Before I talked about this quantity W, which is the number of microstates available, but what's a microstate? A microstate can be defined in a number of different ways. If we were doing quantum mechanics, we'd say that a microstate is one quantum state of the system, but we're not going to do quantum mechanics. It's easier and a little clearer usually to use a classical picture for the movement of atoms and molecules, even though that's not quite right. It's actually a very good approximation nonetheless. Well, in that case, if we're using classical mechanics, one microstate, one mechanical state of the system, one microscopic state of the system, is knowing where every atom is, knowing the position of every atom, and also knowing the momentum of every atom, or essentially the velocity of every atom, right? The momentum is just the mass times the velocity, so they're very closely related. So if it's easier to think about the velocity, then that's a good way to do it. Every position requires 3 coordinates, right? X, Y, and Z positions in space. Every momentum requires three numbers also, a component of momentum along the x direction, one along the y direction, and one along the z direction. So there's 3 numbers for position, 3 numbers for momentum, 6 numbers altogether for every single atom or every single particle in the system. That means that if you've got n particles, you have 6n degrees of freedom in the system. If you've got only a small number of atoms, like in this case only 3, then still it's a fair number of degrees of freedom. 3 times 6 is 18. But if you've got Avogadro's number of atoms, like you usually do for typical chemical situations, then you've got an enormous number of degrees of freedom. So what this is saying is that one microstate of the system is any time you move anything, right? If this is one microstate, and now I move something, move any one of these guys, or move all 3 of them as I did here, then this is another microstate, a different microstate. And now if I leave them all in position, I don't change their locations, like I didn't here, right? All these locations are the same, but I change their momentum, so they're moving in different directions, different speeds, then that's still a new microstate. Anytime I change either the momentum or the position of even one molecule, that's a different microstate than what we had before. On the other hand, a macrostate is a set of usually a very large number of these guys up here, these microstates. So instead of being just one microstate, it's a whole collection of them. And this quantity W that we talked about is the number of microstates in the set. How do we define what set of microstates we want? Well, we look at what the constraints on the system are. If I've got an isolated system like this, then energy, I've got insulating walls, I've got rigid walls that can't change in volume, the number of molecules can't change, all these guys, all these quantities are fixed. That means that I can change things on the inside here, but only in ways that are consistent with these constraints. But I am free to change them in any way that's consistent with these constraints. If I move these guys anywhere inside the volume, so I'm not violating that constraint. If I don't change the molecules, number of molecules, but I move them around, then I'm not violating this constraint. And if I exchange energy, so I make one of these guys go a little faster and one a little slower, but in a way that amounts to preserving the total amount of energy in the system, then any way I'm free to do that. All the ways I'm free to do that constitute the number of microstates, or the full set of microstates that's in this one macrostate. The macrostate is determined by these three numbers, V, N, and U. The constraints determine which set of microstates I'm interested in, and then W is the number of microstates in that set. The ergodic hypothesis is the key idea that we need now. So far we're defining what we mean by a microstate and a macrostate, but now we need to be able to calculate probabilities, and the ergodic hypothesis is the basis for doing that. The ergodic hypothesis says that all the microstates that have the same energy, so for an isolated system, that's all the microstates, period. But even if it's not an isolated system, if it's open to surroundings, so energy can flow in and out, as long as we're talking about the set of microstates that doesn't involve any flows or changes, they all have equal a priori probability. All the microstates with the same energy, whether in an isolated system or an open system, have equal a priori probability. I could talk a lot about where this comes from. It's been investigated at enormous length over the past 100 years or so. But let's just take it as a given right now. All microstates have the same probability if they have the same energy. In that case, we can now calculate probability. W is the number of microstates in one macrostate. That's WT, let's call it, the total number of macrostates. But now I take a subset, some subset of states that I'm interested in. There's some W associated with that too. Then the probability of observing any number, any element within that set is just the number of microstates in that set divided by the total number of microstates. In other words, it's the fraction of all microstates in the set S. Let's look at an example. In this case that we started out thinking about, where we're dividing our box into two pieces, 1 and 2, and we're asking how many molecules are there on one side, how many are there on the other side, then the set that we're interested in is the set of all microstates that has exactly N1 molecules on this side. And once we know that there's N1 on this side, we know that N1 plus N2 has to equal the total, so we know how many there are on the other side also. If I've got 100 and I say that there's 30 on this side, then I must have 70 on that side. And if that's the case, then we can calculate how many microstates are available when I've essentially fixed how many are on one side and how many are on the other. And that's V1 to the N1 power divided by N1 factorial times V2 to the N2 power divided by N2 factorial times each other, because they're both independent, right? The molecules can move on this side, can move independently of the molecules on this side. So every configuration on this side, there's a whole bunch of configurations on that side, this many in fact. And the total number when there's no constraint at all, when I'm not saying how many are on each side, is then just the total volume raised to the total number of molecules power divided by n factorial. And using our rule up above here, W of S divided by W of T means taking this and dividing it by that, doing some algebra, and that gives us this thing that we call the binomial distribution. It's just about the most common discrete distribution that there is. And it's exactly the same distribution that your book talks about, but it's talking about a slightly different case. It's talking about coin tosses. Coin tosses have the same distribution as the number of molecules on the two sides. And you can see that that's the case because suppose that you decided whether to put a molecule on side 1 or side 2 by a coin toss. So you flip a coin. If it's heads, you put it on side 1. If it's tails, you put it on side 2, and you just keep flipping coin tosses and then ask how many ways are there to get a certain number on this side and a certain number on that side, and you can see that it's exactly the same logic. So down here, in fact, this is a page from your book for coin tosses. I've just modified it slightly by renaming the axes, and we've got the number of the probability of seeing a certain number of molecules on side 1 and a certain number of molecules on side 2. And the main point of these 4 graphs is that if you have few molecules, then there's a high probability of pretty much seeing any of the possibilities on each side, right? If I've only got 4 molecules, then the only possibilities are 0 on side 1, 1 on side 2, 2 on side 2, 3 on side, 0 on side 1, 1 on side 1, 2 on side 1, 3 on side 1, or else 4 on side 1. Those are the only possibilities. And you can see, well, yes, 2 and 2, a split of 2 and 2 is the most probable case, and a split of 1 and 3 is the next most, and a split of 0 and 4 is the least probable, but there aren't any really big differences in the probability. On the other hand, by the time you've gotten to n equals 10, now you can have 0 and 10, 1 and 9, 2 and 8, and so on. And now the most probable is still 5 and 5. And now there's starting to be seriously big probability differences between the 5 and 5 case and the 0 and 1 and 10 case. By the time you've gotten to 200, wow, if you want to get as few as, now the most probable case, of course, is 100, 100, an equal split on in both boxes. But if you wanted to ask what's the probability of seeing only 50 on side 1, well, now it's basically 0. By the time you've gotten to 1,000, the most probable case is 500 and 500. And the odds of seeing anything except something very close to 500 is now essentially 0. And what that means is the following, that if you were to look at this system, you have some microscope and you're counting how many molecules there are on each side, and you were to do that over a course of time and record how many molecules you see at each instant of time, if there's not very many molecules, only 10 in this case, what you'll see is a lot of what are called fluctuations. There'll be a big variation in the number of molecules you see on side 1. And that's because they all have some pretty decent probability. None of them really have 0 probability. On the other hand, if you've got 200 molecules in the box, now the fluctuations are starting to get pretty small. Unless you're pretty close to 100-100 split, you're not going to see those cases, right? Out here at 50 or 150, you're just not going to see those cases. All your fluctuations are going to be right around the 100-100 case. And if you've got 1,000, the fluctuations are now even smaller. And what that means is as this number keeps getting bigger and bigger, the fluctuations keep getting smaller and smaller. And if you've got Avogadro's number of molecules, you're just not going to see any fluctuations at all. And what that means is that the number of molecules that you see on the 2 sides of the box is essentially fixed. As far as your observations and your ability to see is concerned, you're going to see, in this last case, for example, you're going to see 500 molecules on this side, you're going to see 500 molecules on this side, and that's despite the fact that there are no forces holding them. The only thing forcing the system to have essentially an equal number on both sides is statistics. It's the law of large numbers. And the bottom line conclusion is that when you have a large number of degrees of freedom, the observable properties of the system, in this case the number of molecules on each side of the box, is locked by statistics alone. There's no reason, there's no mechanical reason why you couldn't have 100 over here and 900 over here. It's just extremely improbable. In fact, even having probably 450 over here and 550 over here is already extremely improbable. And that's with just 1,000 molecules. If you have Avogadro's number, any significant deviation from an equal split is just going to have such low probability that you're never going to see it. All right, that's our lesson for today. We'll pick this up again on Monday.